Hello, smart coder. Nothing wrong with the mic. Mic. So let me pin the link to the contest. We're gonna be doing. Hey, JGas. We're gonna be doing the weekly 388 from last night. So let's get started. Let's start with question 1. Here's the link. Apple redistribution into boxes. You are given an array apple of size n and an array capacity of size m. There are n packs where the ith pack contains apple of I apples. There are m boxes as well, and the ith box has a capacity of I apples. Return the minimum number of boxes you need to select to redistribute these n packs of apples into boxes. Note that apples from the same pack can be distributed into different boxes. Okay, so notice that the sizes are small. This is an easy, but you need to make notice that the apples, the packs of apples don't matter because you have to remove them from there and distribute them in the boxes. So we only care about how many apples you have. So let's this is Java. Sorry about that. We're gonna do it on today. Maybe I can do some in Java, but probably some other day. And then notice that it's pretty intuitive to notice that you want to use the largest boxes first so that you minimize the number of boxes that you need. So you want to get the biggest boxes. If you suppose that you didn't, this is like an argument if it's not intuitive enough. If you used boxes that were not the biggest, then you could exchange one of the boxes that is with one bigger box that you left behind, and the result won't be worse, right? So that means that it's always optimal to choose the biggest boxes. So let's sort the boxes capacity from biggest to smallest, and then we are going to capacity. So we want to put this box, we want to discount this many apples with the capacity of the box, and we have used one more box. This means, and if the number of apples is now a negative or even 0, then we're done, we break. And so this should be it. 2 and 4, good, accepted. All right, so there's not much to say about this one. Here the solution. So the order is n log n. So it's n in the number of apples and n log n in the capacity in the number of boxes, and then we just do one pass at most. All right, so let's do Q2. Maximize happiness of selected children. you're given an array happiness of length n and a positive integer k. There are n children standing in a queue where the ith children has happiness value of happiness of I. You want to select k children from these n children in k turns. When you select a child, the happiness values of all the children that have not been selected till now decreases by 1. The happiness cannot become negative. Okay. Oh. So notice that, so one way to think about this is, so you're gonna be, so whatever happiness, so let's call this H. So whatever happiness of some I, so let's say that you go from I in some order, right? And then you need to discount how many previous rounds you have done. That's what you will discard. But notice that you're gonna discount this regardless of the order, right? You're gonna discard, like in the first one 0, then 1, then 2, and so on until k minus 1, right? So this is for each term, this is how much you will discount regardless of the order, which, by the way, this is k minus 1 times k over 2. But the point is that your score or your happiness is going to be the sum of the values of the k values that you select minus this, which is it's a constant. I mean, when k is given, this is a constant. So that when you look at it this way, it's obvious that you want the largest, the k largest, for to maximize the happiness. So let's do sort. Again, reverse equals true, and I think we can do the sum for I in range of k of we want h of I minus I, like we said, but this could be negative, and in this case we want to cap it at 0. So this should be it. And it works. Cool. Make sure the submission. Lucia, is that? Yeah. Yes, in the argument that I gave, I made a simplification, so I assume that you will never get negative. And in that case, I proved that you want the top. So in the contest, I thought about that argument, and that convinced me that this was the optimal, but I didn't think about the case. I just coded and submitted, and it got accepted. I'm not sure how much it changes, or how to adapt the argument. I'm gonna leave that for the exercise of the viewer. You did something more, something different than this? Okay, so let's move on to Q. No, I did that. Okay. So Q3, you're given an array R of size n consisting of non-negative strings, and find the string answer of n. The answer of I is the shortest substring of R of I that does not occur as a substring in any other string in R. If multiple such substrings exist, answer of I should be lexicographically smallest. Yeah, so when I read this, I misread it. So I got confused because I forgot that we wanted to find the shortest, and I just remembered this condition, the lexicographically smallest. So I coded that and I got a wrong answer because of it. So pay attention to the problem description. Make sure you don't misunderstand it. So here you can see that the sizes are very small, so you don't have to be very but in particular the words are at most 20 characters. So the number of substrings is a square, is in the order of the square of 20, which is 400. So it's pretty tiny. So, but in any case, what I did was I counted for all the substrings of all the words, of all the strings. I counted how many, I add them all to a counter. I counted the frequencies. And so then for any given string, I went over all these substrings and I counted how many times it occurred in all of the strings on the one hand and in the current string. And if that difference was 0, then it means that it only occurs in the, it doesn't occur in the other strings, in the substrings of the other strings. Okay, so that is it's pretty much coding that and doing the whole tie break. That's pretty much this problem. So I think it's useful to have a helper function for getting all the substrings of a string. So substrings of S, and this is just standard all pairs kind of code. So the start of the substring and the end of the substring, which is exclusive. So that is going to give us an iterable of all the substrings. So then we can count all the substrings of S for S in the array. So now we have the count of all the substrings in all the strings. Then we are going to be appending to the result, and for every, we also want the counter of the current string, the substrings. And this is actually a mistake that I made. So I forgot. So I got confused, and I just assumed that the substring would appear once in the current string, which is of course not true. It could appear many times. So that's why then I added this and I got accepted. I got 2 wrong answers in this question. So we're going to keep track of the best, which the default value must be the empty string. So we go over all the substrings in the current string, and if the count in all of the strings of the substring is the same, well, yeah, if it's the same cur count, then we found a candidate. So now all the conditions, which are a little complicated. So one option is that the best, it already has the empty, the default value. In that case, we want to update it. Or if the length of the substring is less than the length of the best, because we want the shortest, or if the length of the substring is the same as the best and the substring, the current candidate comes before the best, right? So in that case, the best becomes the current. And finally, we add this, the best, to the result. And I think this should be it. No, not really. What did I do wrong? So here, cur, what am I getting? Always the empty. Take the first one. Well, not really, right? Because you want the shortest. So sort is not going to give you the shortest first. So if the length is less than, or the length is the same, and this is lexicographically smaller, oh yeah, I know what I did wrong. So here, so I'm counting. Yes, this is not what I want. So I want this, right? Okay, now I got something different. So for S, and so oh, this is S, yes. Okay, now we got it. All right. What if the constraints were bigger? That's a good question. So this code is cubic, I think, because all the substrings are square, that are quadratic, but then we copy the substring and we add it to a counter. So we could make it quadratic instead of cubic by doing some string hashing. Like we could have a hash of the of the substring, a rolling hash. So every time we add a character, we update the hash in O of 1. So that would make it quadratic, because you still have this many substrings. So I don't know what would happen if this was big. I haven't thought about it more than what I just said about the string matching. So that's an optimization. But notice that this is not quadratic in terms of the number of strings, right? So that it is linear in the number of strings. So the number of strings could be much larger, and this wouldn't be, and this would be fast, right? So this 100 here could be, I don't know, maybe 10,000 or something, and I think it would be fast enough, because what I said, this is right. Well, no, maybe no. So 20 cube times 100. Why is it not giving me the 800,000? Yeah. Still, there's still room for making n like maybe 2 orders of magnitude more, 1 or 2. So yes, the bottleneck here is the substrings, I think, and I don't know how to avoid going over all the substrings. All right, so let's move on to seeing coach getting choked is top tier content. It was not a big choke. It was just a little bit. But yeah, I'm used to getting them right in the first try. So I'm not used to debugging in the stream, at least. Okay, so maximum strength of K disjoint subarrays. So we're given an array of integers nums of length n and a positive odd integer k. I don't know why k is odd here. Does it make sense? Well, I mean, it changes something, I guess. But anyway, so the strengths of x substrings. So this is a little hard to understand. But you have to select k disjoint subarrays from nums such that their strength is maximum. And here's the definition of the strength of x subarrays. And notice that it doesn't have to be a partition, in the sense that the subarrays don't need to cover the entire array. And the subarray, so you go from left to right, and you get the sum of the first subarray, multiply it by x, then minus, so the sign is alternating. So here it's a plus sign, here is a minus sign, then a plus sign, and so on. And the sum of the second subarray gets multiplied. So this is decreasing by 1 from x minus 1, x minus 2, and so up to 1. And okay, so you cannot do this. So yeah, this is 10 to the 4. And notice this constraint, which is very interesting, because they suggest, if they tell you that the product of these two things is less than 10 to the 6, it suggests that maybe you can do an algorithm that is that has that order, n times k, and that means k is 100 max. No, not really, right? Because this could be less, this could be 1,000, and it could be 1,000, right? They could both be 1,000 and they satisfy the condition, right? But my point is that 10 to the 6 is within what you, the number of iterations that you can do, the number of sub-problems that you can solve, and in LeetCode. So this kind of suggests that maybe we can try to find an algorithm that is n times k, order of n times k. And then, well, then another thing that you can, another observation here is that we only care about the sums, right? But notice that it's multiplying. So, well, let me write down the expression. So maybe you can do this. We can copy this here. No. Oh yeah, there you go. So notice that you have there you have a sum of 1 times times x, right? But here this is a sum, right? So this is, so let's say this is a plus b plus c times x. So you can distribute this. So you of course can distribute this. So that means that you can handle the terms separately, right? So the contribution of each term, it's independent from the others. You can calculate their value, the value of the contribution of the current term, by knowing the x and the sign, which is determined by the number of subarray. But then the terms in the subarray all can be added separately, right? So that is suggesting a dynamic programming solution, because it's kind of a take it or leave it logic, where you, for each term, you can add it to a subarray or not, or you can skip it, right? But there's a catch, that it's not quite that. It's not that simple, because it is not independent. So you have to also have some indication, some extra flag in your DB state that tells you whether you can, if you add, you can add the current element to the previous subarray, to a subarray that is still open in some sense, right? So let me write it down. So we're going to be doing so max the, well, let's call it best, the best strength. We're gonna do memoization, and we want to know on which element we are of nums. So let's call that I. Then J indicates the index of the subarray, so it goes from 0 to k minus 1 inclusive. And then we're going to have this extra flag that I said that tells whether we can add the current element to an already open subarray, an already ongoing subarray. Okay, let's call it open. And initially it's false because we don't have an open subarray. So if j is greater than or equal to k, it means that we already why is it not best I? No, j is crucial because j is going to tell you, so the terms here are multiplied by this term here, x minus I plus 1. So they depend, the multiplier depends on what the index of the subarray is. That's what j indicates. Okay? So if j is k, it means that we already covered. So remember that the index goes from 0 to k minus 1. So if we get to k, we already found all the. Do you mind no, but this is not the multiplier. It's the index of the subarray. X represents which subarray you are on. No. So X is the number of subarrays, which is called, so it's called K in the problem, and it's called X in this definition. So that's why it might be confusing. But the index of the subarray, here it is implicit. Here it's called I. And this is the multiplier of the term, of the sum, right? And it also determines the sign, whether it's subtracting or adding, right? So the j is crucial here. So again, if the index of the subarray is k, it means that we already covered all the subarrays, so we don't have anything else to add. And then we have the case where we already went over all the elements of nums. So that case is tricky because there are two cases. So we know that j did not got to k yet, right? But it could be. So in that sense, we haven't covered all the subarrays, but it could be that we are in the last subarray and it is already opened. So we can close, it means that we can close it here, we can close it in the end, and in that case we add 0. So if it's open and j equals k minus 1, which is that we're at the last subarray, then this is a valid solution, right? So we return 0 because we don't have anything else to add. But if that's not the case, it means that we haven't covered all the subarrays. And we got to the end without covering, so that means that we haven't found the solution. So that means that here, this is bad. We want to return minus infinity, right? So that's bad. So now for the main case. So we have two options. We take it or we leave it, right? So we add. Should it be return minus inf when j is greater than? No, but we're never getting greater than k because. So, I mean, here we could do this. So we're never gonna get greater than k. I'm not following your comment. We're never gonna get greater than k. When we get to j equal k, we already found the. No, we're not returning 0. So this is a valid case, and this is a valid case, and this is an invalid case. Because here in the else, it means that we haven't covered. I'm not sure how we'll ensure that when then the last group has an element. So I'm saying, so j is 0 based, right? So k minus 1 is the last subarray. So when we got to k, we already closed k subarrays. Do you follow? Yeah, it's 0 base. It's 0 base. When we got to k, it means that we already closed k subarrays. So this is a valid case, so we return 0. Here, there's an exception. If the last subarray is still open and j is in the last, then it means that we can have k. We do have k subarrays. So in that case, we return 0. Otherwise, we return minus infinity because it's invalid. We didn't get to the k subarrays. It's invalid. Okay, so here we have two options. We either take it or not. So if we take it, regardless of whether it's open or closed, our situation would be we go to the next element. We go to the next element. We're still in the same subarray, and it's gonna be open. Whether it was open or not, after we add an element, it's gonna be open. And then we add the term corresponding to this, to nums of I. And we multiply by the multiplier, which is k minus j, which is based on this. This is one base, that's why it's different, but this is k minus j, that's the multiplier. Okay, so this is the first option when we take the element. And then the second option, it's going to be, why is it open, close again? What do you mean? Open. Oh, why is it open, close? So this means that the last subarray is open, which means that we can still add the current element. We can add it to an open subarray. So it means that the previous element is part of the current subarray. So we could add the right. If it's open, it means that we can keep adding elements to the current subarray. And if it is closed, we can skip elements. So now we're gonna see the difference, because here it's the same, but now we have the other option, which is going to depend on whether it's opened or not. Okay, so if it's open, we can close it, which means we can the I element to a subarray, but it's going to be the next subarray. So we close the we close the current subarray, so we get to the next index of a subarray, and we're still in the ith element because we could open a new subarray with this element, and now we are closed. Or if we are not open, then that means that we can skip this element and still and go on. Like we skip this element and we go on. We don't close anything because we are already closed. And now we return res. And this is it. But this will give me memory limit exceeded. Let's try it out. Because it turns out this was a good discovery. Memory limit exceeded. So it turns out that I don't know whose fault it is, if it's Python or LeetCode, but every time, so LeetCode evaluates the runtime and the memory for for all the test cases combined, right? So they're gonna be calling this function multiple times, right? But for every call to this function, so we have this best cache, this best function, this inner function which is cached. But the cache, notice that the cache depends on the context here, right? So the nums, it depends on the nums that we got and the key that we got. Those are implicit parameters. So that means that each cache for each call to maximum strength is independent. It's so ideally we would like Python to clear the cache after this is run and the cache is filled. We want it to clear so that in the next call we create a new hash, a new cache, and we don't have all of them in memory. We don't have to keep the previous ones because we're not going to use them anymore. But it seems that like Python does not realize that memory is unreachable and it doesn't garbage collect it. So we have to do it by hand. We have to do it manually, and the way to do it is to, so here we get the result and we return it, but before we return, we can do best cache clear. And now we make sure that the cache does not remain after the call. It gets cleared. And now hopefully we'll get accepted. Right. All right. So I discovered this after the contest. In the contest, I resorted to doing bottom-up DP. This is top-down DP, it's memoization. But with bottom-up DP, you can reduce the memory, because notice that for every transition here, I and J, so the I subproblem depends on I plus 1 and I. So that means that you only have to keep 2 rows of the table, of the dynamic programming table, and that's why you don't have to. So here you have a table for all the possible I, which can be 10 to the 4. But if you do it bottom up, you can get away with only two rows. But I mean, if the memory limit exceeded, it's just because of this mistake that memory is not being cleared, it's not being collected, then I'd rather use this trick than to change my algorithm. Memoization is usually, in my opinion, is easier to understand and to code, and the code is shorter, because you don't have to. You have to be to think a lot about the order in which things get executed. Whereas if you're filling the table, you have to make sure that the values are being populated in when you need them. They were already calculated. Okay. All right. So that's all I have. So thanks for watching. See you in the next one. Bye bye.